Okay, next topic is controllers, specifically PID controllers. This is a very important topic and it has a lot of applications in industry. So the objective is to define a PID controller and in general a controller, and then to explain how PID controllers gains uh, which are proportional gain, integral gain, and derivative gain work. Okay, before we start explaining what's a PID controller, we need to explain what's a controller. So we have a plant, it's a feedback loop. So we have a feedback control of this plant. And as we have studied in this course, we can write down the closed loop transfer function. We can find out the steady state behavior of the system. So a steady state error, final value theorem. We can also, if it's a second order or first order system, try to find overshoot and all those things, settling time and other things. Now imagine if we did all of that and we realized that our system is not desirable for us. We do not like the system. What are we supposed to do? That is the idea of control. You want to change the behavior of the system. So you put a block here, or there are other ways to design a controller to change the behavior of the system. Now, one of the most popular methods is PID controller. It's very simple, it's very easy to understand, it's very easy to learn, doesn't really need as much mathematical understanding, and it works like this. So it has three components: P and I and D: proportional, integral, and derivative. The equation can be written this way in time domain. So you have an error, which is the discrepancy between your reference or reference signal or the desired behavior and the actual behavior or the output of your plant. The discrepancy is the subtraction, or the error is the subtraction of these two signals. Now you feed that error into this thing, this brain, and it's supposed to spit out the correct signal that guides your system or your plant to have the correct behavior. Okay, what's an example? Well, think about driving when you're driving your car. If you're off the road, you your eyes see the current location of your car. So you are measuring the current location. You subtract that from the desired location, which is being on the road. That gives you an error. Now, there is a box or there is a block that receives that error and creates the correct action to fix your system's behavior. Your system or your plant is the car. The behavior is the location or the position which we want to be on the road. Tell me what the controller is and what that signal is. In this example, the controller is your brain, right? So based on your brain receives the error, you realize that you're 3 feet off the road and it interprets the situation or the error, and with the knowledge it has, it says, okay, your brain says maybe you should turn the wheel 10 degrees to the right, or maybe you should do maybe also combine that with pressing the brake a little bit. So as you can see a lot of things in this example, that the unit of measurement do not of the output, which is position here in feet, doesn't match necessarily the unit of measurement of the input, which is I mentioned turning the wheel to the right in angle in degrees. Also notice that the controller here needs to understand that error and having some knowledge about what is the correct action that gives us the behavior we want. So it could have information about the plant. One of the beauties of PID controller is that it doesn't need any information from the plant. So it can be blind completely about the plant. It only receives the error, and then using the error, it creates this signal. So why PID controllers are uh, uh, desirable? What are the applications they have? 95% of control engineering problems in industry use PID control. Probably the room that if you're sitting in a public building or a university, the room you're sitting in has probably a PID controller that, based on the given temperature, tries to keep the temperature on the desired value. Your car's cruise control probably has a PID controller. That's how it's trying to keep the speed of your car at the given value. Even if you open the toilet that you use, even if you open the tank, the water level, which is being kept at a constant value using a float, has a PID controller. PID-based position control is used in a number of robotics applications. PID-based speed control is used in a wide array of industries. So PID controllers are everywhere. PID tuning requires minimum analytical analysis. You can manually adjust the PID gains until you get what you want, or you can use more analytical methods like Ziegler-Nichols tuning rule that we are going to explain later. You can also use roots locus based PID controller design, which later in this course we are going to study. So we have different methods to design a controller. The first step, or the first element of PID controller, is proportional control. So proportional control is when in your PID controller you turn off two of the knobs, two of the degrees of freedoms you have. You turn off the integrator and the derivative terms, and you only keep the proportional control. The idea is that let me go back a few slides. So you turn this off, you only keep Kp times E on. So the U signal here, the action is Kp times error. So it's proportionate to the error. The action you take is proportionate to how much error you have. That makes sense, right? That makes a lot of sense. If I have a bigger if I'm off the road, the more I'm off the road, probably I need to have a bigger action to come back to the road. If I'm off the road by 1 foot, probably the amount that I want to turn the wheel to the right should be smaller than if I'm 10 feet off the road. If I'm 10 feet off the road, I can turn the wheel as far as I can to the right to get back to the road. So that's the idea behind proportional controller. The larger the error is, the larger the corrective action will be. Now, what it does is that large values of Kp create fast response, but the drawback of it is that it's gonna lead to overshoot and oscillations. Think about it. What's overshoot? Overshoot means that I want to get to a value, but I actually passed that value, so I have to come back. That's going to happen in the example of driving. Imagine if you're off the road and then you suddenly turn your wheel as far as you can to the right. What happens is that you might actually come back to the road and then get off the road from the right. You might leave the road again from the other side of the road. So, and then you have to turn the wheel to the left. So proportional control by itself has drawbacks and benefits. The benefit of it is that the response is fast, but the drawback is that it increases overshoot or leads to overshoot and oscillations. Let's see an example. I have the system and I try 3 different proportional controllers, 0.1, 1, and 10 as the gain. Look at what you see here. The response as I increase KP gets faster. So the green here is faster than orange, orange is faster than blue. How do I know that? Well, look at the first time your wave reaches its final destination or final value. For the green wave is here, almost like very close to 0. For your orange wave, it's here. And then for blue wave, it's probably here, almost 0.25, so it's slower. Increasing KP, increasing the gain, proportional gain, is increasing the speed, but it also is increasing the overshoot. So see how oscillatory the green is here. Let's see an example. This is based on the lab that we have. We have the servo system in the lab. We have, it's a first order system. If you want to measure, if you want to look at the speed, if you want to look at the position, it's a second order system. Now we want to have a proportional controller. What happens is that the servo response tracks the desired servo angle well. So this is the desired value, desired servo position. We give 0.9 radians or 1 radians, and then we are trying to observe what happens with the servo system. At the end of the day, it does what it's supposed to, but it has overshoot. Something else that we care about in control is that we also need to care about that control signal we created. Why does that matter? Imagine in the example of driving, imagine if I'm off the road, on the left of the road, and imagine if I do the math and I say, okay, maybe I should turn the wheel 700 degrees to the right. That doesn't make sense, right? So we have physical limitations on the control signal or control effort. It can't be whatever we want. It needs to make sense. We don't want to have spikes. We don't want to have really big values. We want to have smooth behavior. So the takeaways from proportional control, the benefit of it is that it's simple, it's good enough for many systems, and it increases the speed of the system. The drawback is that it can result in steady state error and large overshoots. Now, let's answer these questions. For proportional control, increasing KP will cause the increase of percentage overshoot and rise time. Is this correct or not? It does increase percentage overshoot. If I increase KP, percentage overshoot will increase. How about the rise time? So increasing rise time means that your system is becoming slower. That is false. Increasing KP will make your system faster, which means the rise time would decrease. Second question, what are some of the reasons why proportional control alone might not be enough to give you a satisfactory response? Too much overshoot, slowed down output, or minimum steady state error? Too much overshoot, right? We don't want overshoot, and that's what the proportional control is giving us.